Okay, so recording has started. I'm just gonna wait a few more seconds to see if the number stabilizes for participants. Kaitlin, are you Canadian?
No, I just did my PhD in Toronto.
Just a little side.
I know, yeah. It's good. It's served me well over the last 10 to 15 years for people to think that, though. It's nobody's ever, no one ever thinks worse of me while they're confused and think I'm Canadian. So I myself of that notion.
Sounds good. All right, so it looks like numbers have stabilized for now. So I'm gonna go ahead and introduce you and then you can take over. So this week's speaker is Kaitlin Kratter at the University of Arizona. So a little bit about where Kaitlin's been before Arizona. So she got her PhD at the University of Toronto. That's what we're just talking about. Then she was a postdoctoral fellow at the ITC at Harvard, followed by a Hubble Fellowship, which was cut short, it looks like, because then you began in 2014 an assistant professor position at the University of Arizona, where she is now an associate professor. So Kaitlin's research really focuses on the formation and evolution of both stars and planetary systems. She's used for these studies computational and analytical techniques. And currently she's focusing on binary star systems and their planets. And I believe that's what she will tell us about today. Go ahead, Kaitlin.
All right, well, thank you. And thank you all for making time at the very end of your week to listen to a little bit more science. So I will try to do my best to keep you engaged late on a Friday, though I know we're all getting to be zoomed out. So the good news is by the time you're done with this talk, it'll be nearly happy hour time for you, and you can go celebrate as you see fit. As Deanna said, I work on a range of topics related to the formation of stars and planets. And today I want to talk to you about sort of the in-between in the spectrum as we transition from thinking about how binary stars form and how planetary systems form. And from looking at the composition of the department here, I understand that many of you are physicists, and so maybe not as familiar with some of the detailed astronomical theories related to these items. So I'm going to try to start out with some basic summaries of why these topics I think are interesting, how we think these objects form, and towards the end I'll get to a little bit more technical details on some of our current work on the subject. And I'll just highlight here that this work has been done in collaboration with several other people shown here. Maxwell Moe has led a lot of the work I'll be talking about, who's a postdoctoral fellow here at the University of Arizona. Rachel Smullen is a recent PhD graduate who's actually moved to your neck of the woods. She's at Los Alamos now. Aaron Lee, who's on the faculty at St. Mary's College in California, and Stella Offner, who's on the faculty at the University of Texas, Austin. So why should you care about binary star systems, or systems that are composed of a star and maybe, in some of these cases, another ambiguous object that might sometimes be more like a planet? I'd argue that they're really fundamental to not just all of astronomy, but all of really astro and physics, because binaries really tell us a lot about the scales of the universe. They can inform us about things as exotic as dark energy, even through the information they give us about dark energy, the standard model of particle physics. They can tell us about exoplanets. They can tell us about nuclear physics, and they can tell us about general relativity. So I think it's hard to find another astronomical phenomena like binaries that cover such a wide swath of the physics that's important to us. So let me just try to justify why I have claimed that binaries can tell us about this diverse array of physics. So let's consider a few things. So first of all, let's think of one of the earliest confirmations of general relativity. That came through observations of something known as the Hulse-Taylor pulsar binary, which are two compact objects in a tight orbit about one another. And the predictions of general relativity suggested that because their orbit was so compact, that the emission of gravitational waves would sap energy from the system and cause the orbital period to decay. And that's precisely what's being shown here in this curve. the cumulative shift in period as a function of time from 1975 to 2005. And you can see the red dots are the observations, the blue curve is the prediction from general relativity. So brilliant confirmation of the existence of gravitational waves. I also claimed that binaries can tell us about dark energy in the standard model, and that's because they help tell us about distance scales in the universe. There is a phenomenon in astronomy known as a type 1a supernova. This is an explosion that is extraordinarily bright. You can see in this image of an entire galaxy here, this point of light is a supernova that has just gone off, and it's swamping the light from the rest of the galaxy. Type 1a supernova are driven by binary stars. There's still some uncertainty as to the origin of the exactly how the binaries interact to produce this, but we know they come from binaries. And it's with these supernova that we've been able to measure distances out to very, very far away from us in the universe and illustrate that the universe is not only expanding, but expanding at an accelerating rate. Without type 1a supernova, we would be missing a fundamental probe of this scale of the universe. Binaries can also tell us about general relativity through the existence of stellar mass black holes. So the way that we confirm the existence of stellar mass black holes is when we detect a normal star that's in orbit around what appears to be empty space and turns out to be a black hole. Of course, you're probably all familiar with the phenomena of, from LIGO, the direct detection of gravitational waves. Again, those are coming from either binary black holes born from binary stars or other compact objects. And finally, exoplanet characterization. As I'll talk about in a little bit more detail in a couple minutes, the way that we are able to infer many of the properties of planets outside of our own solar system is only when we can make very detailed measurements of the properties of the stars that they orbit. And the way that we're able to obtain properties of stars is when we benchmark them with a special type of binary. And I'll just point out that, in fact, 3 of the things I've listed on this slide actually have won Nobel Prizes in physics. 2 of them, the gravitational wave conformations, and most recently exoplanets, which I'm arguing are really reliant on binaries. So what much of this sort of relies on is sort of what I consider one of the most generous things we have in the universe as astronomers, which are spectroscopic eclipsing binaries. So these are a special type of binary that arise out of sort of something that's an observational coincidence. They are binaries that we can detect in 2 ways that we often see binaries in astronomy. One is via radial velocities. So this is just the Doppler shift effect, where the 2 stars are orbiting one another. And if there's a component of velocity along the line of sight, that causes shifts in the colors in their spectrum, so individual lines, for example. And because those shifts occur periodically as the stars move back and forth with respect to our line of sight, we can measure the orbital velocity and period of the stars. If those 2 stars also happen to undergo eclipses, which is shown down here in this movie, where one star passes in front of the other and blocks out some of the light, by combining the data from these 2 techniques and simply knowing Newton's laws of gravity, we can actually infer almost everything we would want to know about the physical properties of the stars. We can get their mass ratio, their individual masses, we can get their radii, we can get their orbital period, we can get their physical distance, so we know how far away the objects are. And that means that we can benchmark all of our physical models, because we obviously are measuring how much light is coming from them, we're measuring their spectrum, we're measuring their temperature. And so these special systems allow us sort of to field test all of our theories. And this is where I would say that binaries are really fundamental to our understanding of nuclear physics. It was only by making these measurements that we were able to prove that nuclear fusion had to be at the heart of what was supporting stars like our own sun. And so this combination of things, I think, illustrates why binaries have become so powerful in astronomy and indeed the rest of physics. So now a quick outline of the rest of the talk. I want to start out by giving just a quick summary of what we think we know about how these systems arise, where you have 2 stars in orbit about one another. I'll then transition to talking about things that are also objects orbiting one another, planets and stars. It's just that the mass of one of them happens to be small. And I'll try to describe how their formation mechanisms, even though all that's changing really is mass, can be quite different. And then I'll address this issue in detail as how do we actually define the difference between these objects? I don't think it's just phenomenology. I think it really informs what we know about the universe. And finally, I'll talk about how recent large-scale surveys in astronomy have really helped inform our theoretical models by providing robust statistics on a large number of systems. The plot that I'm showing here is just illustrating that these objects are really, really common. So on the x-axis here, you see primary mass measured in units of the mass of the sun. And on the y-axis, you just see the multiplicity. So how often are these objects found with companion stars, either for mass ratios above 10% or mass ratios above 30%. And the takeaway point here is that this number is relatively large, 50%-ish on average at the low end, rising to over unity, which means that if you're looking at stars like our sun down here, about half of them have a stellar companion. So our sun is neither usual, is not unusual for being alone, but it wouldn't be surprising if a star like our sun had a companion. And if you're talking about the most massive stars in the universe, things that are 10, 20, 30 times the mass of the sun, then we would typically expect that they have not just one, but maybe 2 or 3 companions on average. Okay, so how do we think these objects form? I'd argue that there's 2 modes of binary formation, what I'll call sort of filament or core fragmentation and disk fragmentation. So the first, filament or core fragmentation, arises on relatively large scales, things that are thousands, at separations that are thousands of times the distance between, say, the Earth and the sun. And we think that in general, stars form in these turbulent, messy clouds of gas and dust, and that's what I'm sort of illustrating in these pictures down here. These are 2 numerical simulations of star formation. And we think that stars, binary or single, arise in these dense filaments where, through combinations of shocks, magnetic field structures, and gravity, of course, gases come together to reach densities high enough to overcome other forces and collapse onto itself. And sometimes within these filamentary structures, we get not 1, but 2 bound clumps. And the details of how that happens are still something that is an active area of research. The second mode of binary formation, maybe to people who don't think about stars versus planets very often, is going to sound a little bit more like how we think planets form, which is that you form a star, and then due to conservation of angular momentum, as gas and dust collapse down onto that star, you form a rotating disk, and inside of that rotating disk, a secondary object is born. In the case of binary formation, what happens is that that disk becomes so massive that the self-gravity within that disk actually causes collapse. And I'll talk a little bit more about that in detail in a moment. Just to zoom in on one of these fragmenting filaments for the first mode of star formation so you can see what I'm talking about, what we find in these simulations is that at the sort of intersections of different filamentary structures, we end up getting multiple objects that are bound to one another. And in fact, we don't just form 2 stars that are bound, sometimes we form 4. That's what's being shown here. It's actually a quadruple system. Nature is messy and creative, and so we often find that something may form in a quadruple with an arrangement like this, but then the interactions with the background gas and the gravitational perturbations of other objects can cause fun things like partner switching, and so this ends up, with undergoing some interesting dynamical interactions. For any of the sort of astronomy experts in the room, I implore you not to call this process capture, because these objects begin their lives well bound, and then they undergo orbital evolution, which is not the same thing as taking 2 unbound things and having them dissipate energy and become captured into orbit about one another. We also know that in the course of these interactions, the orbits of these objects evolve. In fact, most binaries that we observe in the universe exist on scales that are kind of comparable to the scale of our own solar system, several tens of AU separation. And we can see in these 2 illustrations from this simulation work led by Aaron Lee that due to dynamical friction with the gas, these stars actually migrate closer and closer together over very rapid timescales in an astronomical sense, fractions of a million years, which compared to the time it takes to form a star is relatively short. It's sort of on the timescale that the star is growing. Compared to the lifetimes of stars that are many, many billions of years, this is exceptionally short. So they form and very quickly move onto orbits that are what we observe for most of the binaries that we see today. The model of this simple dynamical friction model here is shown in red, and the simulation data is shown in black. Now, this isn't something that we just make up in our large-scale computer simulations. This is something that we actually observe in the universe. This is an illustration of a system like this coming from observations with the Jansky Very Large Array, which may be a surprising, maybe some of you have been there. It's not so far. There's actually, we think, 4 stars bound to one another. They live in this dense filament of cold gas and dust, and to the best of our ability to make measurements, appear to be gravitationally bound, although that's obviously a challenging thing to do observationally. Again, this is an ammonia, for the experts in the audience, this is a ammonia emission. Now, the second mode is something that we also have a pretty good basic understanding of physically. It actually arises from a well understood in a wide range of contexts in astronomy, linear instability, which is often called gravitational instability. And it's a, simply put, a hydrodynamic instability that arises in a rotationally supported disk when self-gravity, illustrated in this figure by this red arrow. So there's sort of gravity coming from 2 sources, from the central star. It has a component sort of directed towards the star and a component directed downwards. This is what sets the sort of hydrostatic equilibrium in the disk. And then the gas itself can exert a gravitational force on all the other gas surrounding it. And if enough mass is packed in, that gravitational force can become strong. That is normally opposed by pressure, again, which is what would keep the disk in hydrostatic equilibrium, just like our Earth's atmosphere. And then the other force that is involved is the sort of the support supplied by the rotational shear that you get in a Keplerian disk. Recall that the rate at which something is moving in response to gravity is a function of the separations, scales like 1 over root r. And so as you go further and further away, you get slower and slower, and this shear effectively stretches out any perturbations as they start to grow. You can do a simple linear analysis. This is what the dispersion relationship looks like for this system. If we consider the axisymmetric mode, where m is equal to 0, again, this is similar to any WKB analysis you would do in any context in physics. You can derive a simple criterion at which you get growing modes, simply by finding where this becomes imaginary. And it turns out that this is a simple function of properties in the disk, like the temperature, the orbital frequency, and the surface density sigma. We can rewrite this in a simple way in terms of the basic properties of the system, which I think is really useful, which is basically an order unity coefficient times the ratio of the mass in the star to the mass in the disk, times the aspect ratio, or the height, the thickness of the disk relative to the radius. So is the disk very, very puffy, or is it very, very flat? And we find that growth begins, at least in this local axisymmetric model, when this quantity becomes order unity and then drops below it, is where the instability kicks in. And so we think this simple linear instability is effectively what's responsible for this second mode of binary formation. As with the first, we actually have physical evidence for this in the universe now. It's not just something that comes out of our pen and paper calculations, or indeed a numerical simulation, as I'm showing here. We have observed a disk that is undergoing this process. We can see the same sort of spiral arms, which are a manifestation of this instability. And then we observe 3 objects that have formed, we think, in this same disk via this process. And this is ALMA dust continuum emission at 1.3 millimeters, again, for any ALMA experts in the audience. And so together we now have, I think, a pretty complete picture where we understand the basic origin of these objects, and we've observed examples of this fragmentation in process. Now, a final thing that we've learned recently, and I'm going to point this out now, and I'll come back to it towards the end of the talk, is that there's actually a really interesting, strong correlation that's been observed between the type of gas out of which the stars form and how often we make binaries. Now, in astronomy, we have a concept called metallicity. which is just how much of the gas is not hydrogen or helium. So anything that's heavier element than hydrogen or helium, we call a metal. And that tells us about sort of how many generations of stars have formed in this gas. And from the perspective of understanding the origins of stars and planets, it's also a proxy for how much dust and how optically thick the gas is. And what we found by compiling data from a wide range of astronomical surveys is that binaries form preferentially in gas with very low metallicity. So this is metallicity on the x-axis here, measured in funny astronomer units. The sun is, by definition, over here at 0, and going down to negative numbers, it's a logarithmic scale, is decreasing the amount of stuff in the gas that is not hydrogen or helium. And you can see the binary fraction is increasing as we go to low metallicities. And I'll come back to this as important in a little bit. So I want to take a break here and just pause for any questions. I know that we all have many distractions, and so I've put up little thumbnails of the slides that I've shown so far in case you were, you know, taking the knife out of your 3-year-old's hand while I was saying something and you have no idea what you missed. So if anyone has any questions, I can try to look at the participant list, or maybe Deanna can, just before I continue talking.
Okay, so it looks like Dominic has a question. Go ahead, Dominic.
Yeah, my question is, are binary orbits typically stable or unstable over the order of like 1 billion orbits, or no?
It's a great question. So I think it depends on what you mean by stable. So, right, we know that the two-body problem is perfectly solved. So if I take 2 stars and I put them in orbit about each other, and there's nothing else in the universe and no other physics, they will continue on that orbit unchanged forever. Now, if you add in other physical effects, that can obviously change. So if you're asking, do binary orbits evolve over the lifetime of the universe, the answer is certainly yes. They evolve if they are perturbed by another object. They can evolve if they are close enough to one another to excite tides, like the Earth-Moon system, which is also evolving. If you want to know about stability, like if I take 2 stars and put them together, are they going to fly apart at some point? The answer is sort of the same, in that if you add something else into the system, yes. So for example, if you have 2 stars and one of them explodes as a supernova, that can cause the system to become unbound and fly apart because mass is lost from the system. If you add other stars into the system, so let's say you have 3 stars in orbit, there are reasonably well understood constraints on how those orbits can be configured in order for the system to be stable or unstable. Does that answer your question?
Yeah, it does. Thank you.
I have no questions.
Hello?
And now on the page 9, what is the difference between the 2 pictures?
Can you repeat that?
I say on the page 9, what is the difference between the pictures?
Are you asking about these 2 pictures?
Yeah. No, these 2. This previous, page 9, previous.
Which 2,
Yeah, this one.
this is time. So this is one.
No, this is, yeah, this one.
This is just two different binaries that form in the simulation. So this is just 2 examples of binaries that are formed in the simulation, move closer together due to this interaction with the background gas, and we're showing that the model works for both systems. Does that answer your question?
Yeah.
Great, thanks. Thanks for clarifying that.
I don't see any others, so.
All right, so that was my very, fire hose attempts to explain what we think we know about binary formation. And now I'm going to do a little bit the same thing for planet formation. And I just want to emphasize again to those of you who don't think about these problems as much as I do, why understanding planet formation is so challenging. In some ways, you might think it was easier than understanding something like binary star formation because, of course, we live on a planet. We are surrounded by other planets in our solar system, so we have some really good local and even sort of laboratory evidence of the process of planet formation coming from things like meteorites and probes and landers and things like that. But in terms of understanding it broadly and understanding exoplanets, what I'll talk about now is that we know that planets form from a very small, at least by mass, component of the protoplanetary disk, which is this thing called metallicity. It's the stuff that's not hydrogen and helium, right? The Earth is not primarily composed of hydrogen and helium, it's rock. And in the sort of background interstellar medium, the sort of background gas out of which stars form, that ratio is 1 to 100. Right, so it's a 1% by mass that at best is going to go into these planets. And maybe even more frustratingly, the building blocks of planets are something that we cannot observe, right? We think that, at some stages, these dust grains, they grow, and I'll talk about this more in a minute, through stages where they are, maybe hundreds of meters, kilometers, hundreds of kilometers across. And those are objects that outside of our solar system we're not ever going to be able to see because they just don't emit light efficiently. So we're sort of blind to one of the most important phases. Another big challenge is that one of the things that's really crucial for understanding planet formation is a detailed aerodynamic understanding of how solids and gas interact. This is a very common problem in fluid dynamics in many different applications, and it's very important in our understanding of how planets arise. And finally, from a demographic perspective, planets don't live where they are born. So we can't look at a planet and say, this tells us about the conditions where it formed in the disk. They can move around through interactions with gas and other planets, and so the final systems, of which we have a very detailed census now, don't paint as clean of a picture of the planet formation process as we might hope. I'm just going to quickly show a kind of an illustration of one of these protoplanetary disks with the star at the center. And what you can see here is just labeled all of the different ways that we can make observations about these disks. We can learn about the atmosphere of the disk from, say, looking in the infrared. We can look at the near infrared and UV and optical to learn about this interior regions of the disk. In millimeter and sub-millimeter wavelengths, we can observe both certain lines in the gas and also the dust. So we have, I made it sound like it's very hard, but we do have a lot of information now, especially with facilities like ALMA that have come online in the last decade. So how do we think planets form, and how is this different from what I've described about binaries? So I'm going to tell you about the sort of classic theory of core accretion that arose starting in the early 1980s and has really, I think, been better and better developed over the last several decades and shown to have, it's held up very well as we have gone from having 8 or 9 example planets to many thousands, despite what maybe you've heard if you've read a popular media article, which likes to suggest that we have no idea what we're talking about sometimes. So the basic parts of core accretion are that we start out small. When I talked about binary formation, we talked about starting with a sort of top-down mechanism where you have these diffuse clouds of gas and dust and they collapse to make objects. With planets, we're going to go in the opposite direction. We're going to start out with tiny, tiny dust grains, things that are millimeters or centimeters in size, and they're going to start to grow and clump together. When they're very, very tiny, electrostatic forces rather than gravity can allow them to grow. But this process only works up to things that are still, nearly microscopic, maybe centimeters at best in optimistic cases when you've got really, fluffy ice grain particles. In the classic picture of core accretion, essentially a miracle happens here, and somehow we get from objects that are centimeters in sizes to meters, hundreds of meters, and kilometers, and then we call them planetesimals. And the classic theory of core accretion doesn't really have a good explanation for how you jump that barrier from very, very tiny dust grains to large macroscopic objects that would be like asteroids in our own solar system. And one of the reasons why it's challenging to understand that growth phase is, something you're very familiar with. If you take 2 rocks together in your backyard and you throw them at each other, they don't stick because the force of gravity is not strong enough to overcome the repulsive forces from when they collide with each other. And now, gravity environment in a protoplanetary disk is very different, but the same thing effectively holds true. If you throw two rocks at each other in a disk around a star, they will fragment before they stick when they are larger than, again, probably a few centimeters. And it's not until these objects get to sizes that are like our asteroids that gravity is enough to hold these piles of little rocks together. But in the classic picture, that's just sort of overlooked until you get to that scale where gravity becomes important. And then these individual kilometer to 100-kilometer sized bodies begin to collide with each other because they now can interact gravitationally and grow to form the cores of planets via these collisions, which, as illustrated here, can sometimes be violent. And of course, this is something we have good evidence for in our own solar system in the form of craters, right? We see evidence for these types of collisions. We know that they happen. And then finally, the last phase is that some of these things that start out by growing these rocky cores will get big enough to start eating up gas from the surrounding nebula. And it's those planets that are big and good at eating up gas that turn into the gas giants or ice giants even, when they can collect a substantial amount of non-rocky material. Of course, not everything is going to turn into a gas giant, so many of these things, like our own Earth, don't accrete a substantial atmosphere from the surrounding protoplanetary disk. And indeed, the atmosphere of our own Earth today is not what we call primordial. It's not formed from what was initially in orbit about our own sun. It's formed by outgassing and other geological effects on the surface. So let me see. I just want to point out that even though the theory I was talking about was mostly developed in the 1980s and 90s, there's been a lot of progress in the last decade or so where we've solved a lot of the problems that I sort of glossed over in that initial picture. For example, we now have a really robust mechanism to make planetesimals that actually relies on that aerodynamic interaction I described between solids and gas, where instead of having things sort of grow smoothly through that size distribution, they can clump together and gravitationally collapse to get from centimeter sizes to, say, hundreds of kilometers directly. And it turns out that those little particles can probably be very important in growing the planetary cores. So it's not just kilometer-sized bodies colliding with each other to make something like the Earth, but it might be some part collisions between things that are like asteroids, and then also those asteroid-like things accreting things like centimeter or meter-sized bodies. So yeah, I'm just gonna skip past this because I think I'm going slowly enough that I want to move on, and I will again stop here and ask if people have questions. I know that was, again, fire hose quick introduction to planet formation, but the main thing I want people to understand is that it's a really bottom-up process where you start out with small, tiny grains and grow to form things like our Earth and Jupiter.
Okay, I have a question, I think, that I'm gonna read out loud. It's in the chat. Describing the size of objects required so that they stick together via gravity, are you implicitly assigning a temperature to the dust, calculating an RMS velocity, and requiring that this be low enough compared to gravitational potential energy?
Okay, so let me see if I can unpack that. So
it's not, yeah, I can repeat it if you want.
Yeah, so I effectively, I think the answer is yes, except that the temperature the temperature is actually not what matters. It's the, well, it's the velocity dispersion at some level. So if you're asking about dust grains sticking together when they're very small, that's not gravity, that's electrostatic forces. As things get bigger and bigger, the reason that I'm arguing that it's difficult to have things coagulate is because the velocity dispersion, which is being set by other processes in the disk, not temperature, because these are now macroscopic objects, that's set by turbulence in the disk, the eccentricity of the orbits, the interaction with the gas. So that's what you would compare to the gravitational binding energy. And then when you talk about very large bodies, things like, again, 100-kilometer bodies, again, you're comparing not the temperatures of the physical bodies because they're so large, but you're comparing their relative velocities. So did that answer the question?
I hope so.
Okay.
The person can, oh, they said thank you, so.
Okay. Yeah, and we can, there's, I mean, that question of how you decide that is actually, it's quite interesting. There's been a lot of both laboratory work and, you know, numerical experiments to try to understand exactly how that process evolves as the sizes and velocity dispersions evolve. So hopefully I've captured the essence of it for you, though. All right, I think if there's no other questions on this part, I'll move on and start trying to put a couple of these things together. So I apologize for my cheesy title here. I think like many of you, I've spent too much time trying to entertain toddlers over the last 6 months and coming up with new lyrics for simple tunes like Twinkle, Twinkle, Little Star. But as I said at the outset, I do think it's really important to try to understand what the difference is between these objects. And, you know, I think naively when somebody just asks, what's the difference between a planet and a star? It sounds like a trivial question. It's like, oh, a star's like our sun and a planet's like Earth. But the problem, of course, is that there's objects that exist in kind of the in-between, things that are, you know, maybe a few times the mass of Jupiter compared with, you know, or things that are maybe a 10th or 100th of the mass of the sun, right? Those two scales start to merge. And there's an object in astronomy in between called a brown dwarf, which is something that's pretty much like a star, except that the gravitational potential generated by the amount of mass that you know starts to collapse isn't sufficiently strong to create the necessary conditions in the core to ignite hydrogen fusion. So that's typically what we think of as a star, is something which starts fusing hydrogen at some point in its core because the gravitational potential is strong enough to generate the high density and temperature conditions at the very center to ignite fusion. In a brown dwarf, it's too low in mass and that never happens. So it's not quite a star by that definition. And then but it is, you know, our standard definition would say it is massive enough that the conditions in the core ignite deuterium briefly. So you get a very, very short-lived phase of burning of deuterium, and then it dies and it just cools off for the rest of the universe. A typical definition of planet is something that never even gets big enough that the conditions at the center of the core allow deuterium to fuse. And so it's just dead. It just forms and it just cools forever, you know, modulo other sources of heating like, you know, radiogenic material and things like that. Now, the problem is that the processes of formation I just described, either large-scale gravitational collapse or the buildup from little tiny particles to things that get bigger and bigger and bigger, those physical processes have no way of knowing what the conditions are for nuclear fusion, right? Those two sets of physics are totally disconnected. So we have a definition that relies on our detailed understanding of nuclear physics. And in fact, it's not a clean line in mass because it depends on the composition of the gas and things like that. And then we have these formation models that don't know anything about that. And so the question is, how do we reconcile those things in understanding the origin of these objects, especially the ones that are right at that boundary where they're kind of a little bit bigger than what we think of as a planet, but they're smaller than what we normally think of as a star or brown dwarf. Now, when we're talking about these objects, I'll point out that in general, these may not be very common. There's not a lot of objects that reside in this in-between that are, you know, 5 to 10 times as big as Jupiter or 20 times as big as Jupiter. And so that's good, right? Whatever way we want to make them, they're not the most common thing in the universe. And so the question though is, if I'm looking at, say, an object that's really close to its host star or really far from its host star, that's right at this in-between mass ratio, how do I tell if it's like a Jupiter that formed by this bottom-up core accretion process, or if it's a brown dwarf, something that's like a failed star? So it's like a binary, but the mass just never got big enough. So we can start to look at these large data sets to try to tease out trends in the properties of the stars that these companions orbit. And that's where I think we can gain a lot of insight. So what I'm showing you now is some recent work led by a former recently graduated student here in Arizona, Kevin Wagner, who was looking at the relative occurrence rate of these sort of in-between objects, not quite planets, not quite stars. And he was looking at ones that lived at sort of wide separation, sort of tens to hundreds of astronomical units. And so we have relative occurrence on the y-axis and the mass measured in Jupiter masses on the x-axis. So for reference, stars, typical like a proper star burning hydrogen, starts over here. Things in here are in that deuterium burning regime, and below, 10-ish Jupiter masses is where things no longer, no matter how they form, they no longer have enough density and temperature in their core to fuse to undergo any sort of nuclear fusion. And what he found is that there's this sharp uptick in the occurrence rates, the frequency with which we find these objects, as you go to lower and lower masses. And this is sort of what we would predict if things right where this uptick starts arise from the bottom-up process, where, remember, you have to do a lot of hard work to get things to start growing and get bigger and bigger and bigger when you're starting bottom up, which suggests that for everything you would form that's 5 to 10 times the mass of Jupiter, you normally would have formed something that's maybe only 1 or 2 times the mass of Jupiter. And as you go to these larger and larger masses, you basically get a distribution that maps onto what we see coming in from the other side, from more massive stars and brown dwarfs. And so he is trying to illustrate that by looking at predictions from standard core accretion models, these dashed and solid and planet occurrence rates. That's what's being shown in these 2 black lines. And then the dashed line is showing sort of what you would predict from these, either the statistics of stars or these more star formation-like models, where you get this kind of flat distribution of these more massive objects. And so this is starting to hint that, okay, maybe it's this division here around 10 where you start to see one mechanism becoming more important than the other. What I think is even more compelling in detail is what we've seen for these companions that are very close to their host star, which may well have formed by the same 2 mechanisms, but just undergone that evolution that I was talking about. Again, this is one of these pesky problems we have with understanding planet formation, is things don't stay where they formed. So there's a lot going on this plot. I'll try to unpack it slowly. On the x-axis, we have the mass of the object that we're talking about, again, measured in Jupiter masses. So Jupiter down here, stars up here. And on the y-axis, what I'm showing is the fraction of these objects that are found in a triple system. Basically, there's another star in the system. There's the primary star, there's this thing whose mass is measured on the x-axis that's orbiting it, and then sometimes there's yet another star in the system. So you could either think that at some end, this end of the spectrum, these are triple star systems, and at this end of the spectrum, they're planets and binaries. And what we found is that there's this jump as a function of mass. If I look at things that look really, that have the mass of something like a planet in our solar system, like Jupiter, they don't very often have a binary companion. And that's consistent with what we've seen from planet statistics overall. If I have one star, and then I take another star and I put it kind of close within sort of the size scale of the solar system, it tends to wreak havoc on the planet formation process. This isn't hard to understand. If you imagine that you're trying to build up mass around one star and I throw another big gravitational perturbation in there, it's easy to see how that could kind of mess things up. And that's what observationally, we've been able to verify, that putting another star inside your planetary system isn't very good for planets. It doesn't mean that they never form there, it's just not very good. So you don't form them nearly as much. On the contrary, when we look at pairs of stars that orbit each other at these same separations, with periods of 10, 20, 30 days, most of the time, they have another companion. So stars that are close to each other like to live in triple star systems. If you go to short enough periods, in fact, something like 90% of very close binaries will be orbited by a third star. And that's definitely telling us something really interesting about formation. So this dichotomy that we start to see in this fraction is saying that things that are down here, maybe below a few Jupiter masses, they tend to behave like the planets. They don't like having another companion in the system. And things all the way up here that are, proper stars, and then maybe, not quite sure if you want to call it a star or a planet, those things are behaving like the stars. They really like to have another companion. And this jump happens right at this, transition of a few to 10 Jupiter masses. And so we think probably this division is telling us again about this bottom-up formation down on this end of the plot and this top-down formation on the right-hand side. And the thing that's really interesting is that on top of this trend in whether or not there's another star in the system, we also see that the gas out of which these objects forms is qualitatively different. And I'm saying different as measured through the metallicity. So how much dust was in the gas initially when you started trying to make your planet or your star? If you look at the, wow, I've terribly confused you all, and I have the two labels, no, I'm missing I have my minus signs screwed up. So if you don't understand what Fe on H means, that's good. Just ignore that and I'll just describe it. I apologize. I have a typo here. For things that are in this core accretion part of the plot, the typical metallicity is significantly more metal enhanced than our own solar system. So you start out with a whole lot of dust. If you look at systems that live out here in this part of the mass ratio spectrum, they tend to live in low metallicity systems, systems that are much less metal rich than our own solar system. So things that require dust to seed the growth of the object prefer very dusty environments, and things that form top down and don't need that seed prefer lower metallicity environments. And so we think that what's going on here is telling us again in detail about how these two processes are different across the mass spectrum. So I want to spend another couple minutes just saying why we think that this mechanism, this top-down mechanism, is okay at forming these big things, but not so good at forming the really small things. And that's because, you know, something that can actually be understood in pretty simple terms from that linear instability that I started out with. And I don't want to go through detailed dispersion relations with you all now. It's way too late on a Friday for that. I'm merely putting this up here to show you that this isn't just hand wavy, right? We can actually work out the reasons why the instability behaves the way it does as a function of pretty simple WKB analysis physics that you'd be familiar with from, you know, a quantum class. The cartoon version of it is as follows, though, which is that gravitational instability, this instability that causes a secondary object to form in a disk, typically that happens given all of the astrophysical circumstances that we understand when the mass of the disk is really quite large compared to the mass of the star. It's getting, or not to be equal to the mass of the star, but maybe tens of %. And what that corresponds to is a disk that's, you know, relatively puffy. And that's why I'm saying when the ratio of the height of the disk to the radius isn't that big, isn't that small. So it's maybe again 10%. As opposed to, you know, 1%, which is something that we would maybe more typically expect in a proto-solar nebula. And the nature of the instability shifts a little bit, but the main way that you can see this is sort of in a simulation that shows you sort of how these two things look. This is kind of what you would expect when the disk is low in mass and relatively thin. You get these little tiny spiral arms, and this is what it looks like when the disk is relatively thick. You get these larger, bigger, lower, basically lower M axis, lower M modes. And if we basically calculate the conditions under which the instability arises in astronomy, this is probably a better cartoon representation. And what that means is that the mass scales at which objects arise from the instability are just too big to be planets, because you're forming in these large, very dense, thick spiral arms, not these small, narrow spiral arms where the mass scale might indeed be something akin to planets. I'm just going to skip this in the interest of time and say that we can actually connect up this idea of fragmentation with the metallicity I mentioned before. So remember, I was saying back on this slide that the objects forming over here tend to like forming in metal poor environments. So the reason we think that that's consistent with this picture of gravitational instability at that end of the mass spectrum is because of the effect that the metals have on opacity. So what I'm showing here again is radius in the disk on the x-axis, and then metallicity. So this is how much dust you have in your disk compared to the amount of dust in the disk around the sun. So the sun is up here, and these things all have less and less metallicity. If you just look at this gray line here, this shows you the line at which on one side of the disk, on one side of the line, disks tend to be optically thick, meaning that a photon trying to escape from the midplane will scatter many, many, many times before it's able to leave the system, and optically thin, in which case you're in the free streaming limit. Photons will escape easily. What that translates to is that on this side of the diagram, disks have trouble cooling down. They stay warm, whereas when things become more and more optically thin, they can cool more easily. And so if you imagine taking a blob of gas in a disk and you squish it and you compress it, right? The ideal gas law tells you that it will heat up. What allows something to continue contracting when you compress it and it heats up is its ability to cool efficiently. And essentially what we found is that when you're in this optically thick regime on this side of the line, it can be difficult for the disk to get rid of its energy and cool down. And when you're on the opposite side, it can be easier for it to get rid of that energy and cool down. And that ability to cool efficiently promotes the generation of an object, because you start to collapse, you cool, and you continue to collapse further and further. And so this is why we think there's this connection between how much metals are in the gas and whether or not you're likely to make a secondary object by that instability in the disk. So for things that form bottom up like planets, you want more metals because that you want more dust, because the dust helps you seed the growth of those bigger dust grains and planetesimals and planetary cores that can then go on to eat up a lot of gas and become a Jupiter. And on the opposite end of the spectrum, if you want to form top down, you want to get rid of more of that dust so that you can cool quickly and radiate efficiently and allow top-down collapse to proceed to form a bound object. And indeed, I'll just return to this plot that I showed at the very beginning of the talk, where we can see this trend in binaries as a function of metallicity, which is both consistent with the division we see between those objects that sort of reside in the in-between between planet-like and star-like, and then it's also reflected amongst the close binaries that we find just, regular stars for, sort of normal mass ratios in the universe, because we think those objects, at least when they're close together, likely formed in the disk as well. And again, for those of you who may be more expert in stellar astrophysics, one thing that's very interesting is this strong trend where binaries are more and more common as we go to lower and lower metallicity. It actually goes away when you consider stars that are so far apart that they couldn't have formed in the disk. And so this opacity effect is likely not important for the origin of the stars. So I'm going to finish up there, and I'll put up a quick conclusion slide in case you have been maybe figuratively surfing the web rather than literally trying to surf the web, like this toddler here. And I'll just try to summarize what I've tried to share with you today, is to sort of understand that binaries probably arise from two different physical mechanisms, both core and disk fragmentation, that there's migration processes that act to change their orbital properties. At low metallicity, close binaries are common, and at high metallicities, giant planets are more common. And that this trend helps us differentiate those objects that reside across that mass spectrum. And the final thing I'll just mention that's kind of fun, and I encourage you to look at Maximo's recent paper on this, is that because of this effect where binaries actually suppress planet formation, it actually can be really important to keep these objects in mind as you go about planning future missions and searching for habitable planets. So I will go back to the thumbnails in case people want to remember what I've tried to talk about today and take any more questions. And thank you very much for your attention.
Thank you, Kaitlin. I'm gonna give you a real clap. So I have two questions in the chat, but let's, hang on, I'll give you the first one, then we'll go to the hands raised, and then if we have time at the end, I'll do the second one. So the first question I got in the chat privately, apparently, is, so the spiral arms that you're showing look like spiral arms in spiral galaxies. Is the galaxy versus the planetary dust system basically the same physical system on different scales? And does the 1/r scaling of gravity predict some kind of universal behavior of all coagulating mass systems so that you often get these spiral arms?
Yeah, so great question. So the instability I described operates in galaxies and in disks. It's the exact same instability. In fact, 2^Q came originally from an analysis of galactic disks, not protostellar or protoplanetary disks. There's a couple differences. So one, if you're looking at a picture like this, in galaxies, what often creates a cartoon picture like this is a second galaxy is actually another galactic companion. And we actually see this in protostellar disks as well, which is acting in a very similar manner of creating a second, quadrupole moment that induces the spirals. Galaxies that look like this, which there are also galaxies that look like this, probably is, very similar self-gravity. One difference is that instead of, do I have Q anywhere here? Instead of the sort of pressure support being due to temperature, it's again due to usually velocity dispersion of the star particles. And there's some really interesting things you can do where you analyze a combined fluid of particles and gas. But it's, again, yeah. So that was part one of the question. Was there another part of the question that I didn't answer? Here's the.
I think that was the gist of it.
Yeah.
And let's see, Dominic has his hand up.
Yes, this might be kind of a hairy question, but given what you've told us today, given some dynamical properties and the metallicity of a cloud, does that mean that we would be able to predict whether it's more likely to form a binary star system or a planetary system?
Yeah, I know. I think the answer is yes. There's very strong trends, and the trends are different for different types of planets. So Jupiter-like planets, close in Jupiters, things that are, further in than our own Jupiter, we find them preferentially around metal-rich stars. If you look at things that are more like our own Jupiter a little bit further out, that preference for high metallicity starts to go away. If you look at small planets, rocky planets like a few Earth radii, those also don't seem to have the same metallicity trend. So there are, but yeah, these trends are very distinct. Now it's a probability, right? There are fluctuations. It's not that every single object has that metallicity and therefore forms something. But probabilistically, you can say if you give me a distribution of, gas clouds with different metallicities, I can tell you statistically what type of systems you would expect to form.
That's pretty rad. Thank you.
I don't see any other raised hands, but I know. Is that someone asking a question?
Looks like somebody's waving. I see a person waving in the screen.
Okay, that person should ask. Go ahead.
Hi, can I? Whoa. I don't.
Kevin, do you want to paste it in the chat, maybe?
All right, try to chat the thing.
Okay. But please mute yourself, or can I do that? Because there's still echo.
I'm putting in a chat question.
I think you can mute.
Okay. While we're waiting for the question is dark matter.
I did claim binaries mattered for everything, so I am totally willing to answer dark matter question. That is totally fair.
That's the question, though. Dark matter.
Just dark matter is the question. What about it? Does it exist? Yeah, I feel confident that dark matter exists. I don't know. I'm trying to think of how I connect dark matter to binaries. Certainly.
Can you?
Obviously, dark matter exists. Huge evidence for dark matter. My question is, whether you have anything to say about dark matter. In particular, you mentioned that a certain class of objects would be extremely hard to observe ever. Could these be as common as to account for a significant fraction of dark matter? And also, what about dark matter that might accumulate and form objects that are in the domain that you've been studying?
Yeah, no. Yeah, no, now I totally understand your question. Great question. Okay, so the short answer is for the objects in the that I was describing, they are indeed matter that is dark, but it's legitimately dark in the sense that it's just an inefficient radiator in the way that, you know, boulders don't radiate very efficiently at any wavelength that we can observe. So they are dark, but they're just normal matter that just happens to be of a size where we can't see it. If you put those rocks, if you make them big enough and you put them close enough to the star, they can be reflective enough that we see them. Indeed, you know, we do observe objects of this size in our own solar system. So we know what we're looking for. It's just we can't see them when they live in other solar systems. We also have pretty good constraints on the amount of mass, because we can make good inferences of how much mass starts out in those systems based on how much collapses down during the star formation process. There's a, you know, some amount of conservation there of mass. Some of it gets blown back out into the molecular cloud, but that's sort of a factor of 2. And so accounting for all that mass, there's definitely not enough to make up anything resembling the amount of dark matter that we need to explain galaxy rotation curves and things like that. We also have pretty good constraints from our own solar system coming from space missions, right, which have made gravity measurements. You know, I think Voyager has done this, right, where there's no evidence for dark matter on these scales in our own solar system. So we don't think that matter forming on these scales could be responsible. And going up to slightly larger scales, we have constraints from microlensing and things like that, where we have looked for, you know, high density, tiny objects that would cause lensing events as they pass in front of other stars. And given the rates at which we observe that, we can't explain the amount of matter that we need to put in, you know, what we call dark matter to, again, explain galactic rotation curves, the, you know, structures of the CGM and things like that. So hopefully that answers your question about dark matter.
Okay, thank you, Kaitlin. So let's, since we're at the hour, thank Kaitlin one more time, but we'll keep the session open in case people have additional questions. So I'm gonna give a clap. Thank you, Kaitlin, for your time. And if you don't mind waiting a few more minutes in case, so people like co-hosts, for example, can't raise their hand. So I want to make sure that they have a chance to ask anything if they want to. And there was another question in the chat that I can pose for you as well.
Sure. Can try that.
So yeah, if any co-host has a question, feel free to just unmute. Otherwise, let's see. There's another question on how do you cool this collection of dust? Are you shedding mass through evaporation or radiating light to the surroundings? I think this was related to sort of the third section of your talk.
How do you
how do you cool this collection of dust?
I mean, it's just thermal radiation of the dust. Is that what you're asking?
I hope so.
Yeah.
This one was another one of those chat questions.
Yeah, I think, yeah, it's just
okay. Apparently, yes. Yeah.
Yeah. Okay. Yeah. That's.
So folks in general, if you want to, feel free to put the questions in the chat to everyone as well. But I think there was one more about metallicity, and it is the metallicity and non-metallicity. Are you referring to the heavy versus light mass of constituent particles? Or are you actually referring to the conductivity of the aggregates?
With metallicity, right, the astronomer definition is very simple. It's just, is it an element that is heavier than helium? So carbon, metal, oxygen, metal, nitrogen, also a metal, silicon, metal. By this, that's all of that is basically being clumped together, and the mass fraction of that you know, relative to hydrogen and helium is what goes into the calculation. To be even more honest, and this is sort of illustrated on some of the plots I was showing, the the thing that's actually used as a proxy is iron. So, this is the measure we have. So basically, it's an abundance of iron relative to hydrogen that's being used as a proxy for metallicity. And in fact, we had a paper that just came out a couple weeks ago, maybe, or a week ago, which looked at not just the abundance of iron relative to hydrogen, but other elements. And we actually see a trend that changes as a function of what element you're looking at, which is really cool because the trend that shows, the elements that show the strongest trend are things like carbon, oxygen, and silicate, which we think are the dominant components of the icy dust grains in these disks. And so the fact that you see the trend stronger in those elements as opposed to iron is sort of more evidence that this is what's going on.
Okay, I don't see any more questions anywhere. So thank you again, Kaitlin. This was great.
Thanks so much. It was fun to spend the afternoon with you. I hope you all get a chance to rest up this weekend and do something fun, go out, explore. Hopefully it's cooler in Albuquerque than it is here.
Yeah, I think so. All right. Have a good weekend as well. Bye.
Thank you very much.
Thanks.
Thank you.